Okay, our fifth and final lesson on this unit on modular arithmetic, and it's going to focus on Fermat's little theorem. But before we get to that, let's just recap a couple of important properties here, and that is that if we have A equivalent to B in mod M, then this important property here that we can raise to the power of n both sides, and we maintain that modulo result. Also, that if A is B mod M and C is in D mod M, then we got that AC was equal to BD mod M. So we're going to use those together with Fermat's little theorem, which I will state now, to solve some remainder problems. So Fermat's little theorem is a cute title for something that's quite useful. Fermat's most famous for his Fermat's theorem that tried to prove that there was no, this is just as an aside, no integer value greater than or equal to 3 that solved this equation for integer values of a, b, c. So we know that this is a familiar looking one for equation for powers 2. That's Pythagoras Theorem, a squared plus b squared equals c squared, where c is the hypotenuse. Lots of Pythagorean results there. 3 squared plus 4 squared equals 5 squared. So there's one ABC integer solution that works. And we know that through our work with Diophantine equations, we know that for power 1, there are many solutions for ABC. I'm there referring to AX plus BY equals C. Now, and finding the integer values for A, B, and C thereof, there are infinite number of solutions there. But for 3 and above, powers of 3 and above, not so many. In fact, none. But finding the proof for the fact that there are no solutions for powers 3 and above for n, that was Fermat's theorem that was being solved in the last decade. But very famous work around that. But Fermat's little theorem is this, and it looks like, okay, quite a nice one. A to the power of p will be equal to, or the equivalent of, a in mod p when p is prime. For p prime, and an integer. Okay, so this is a really important result. When p is prime, a to the power of p is congruent to a. And from that, we get perhaps the more useful result that dividing both sides by a, we get this result. Now, we know this from earlier work, that if we can divide by, we were dividing by d, remember, that divide by d, and this changed, didn't it? If this changed if the GCD of dp was not 1, or d and p weren't coprime. Now in this case, because b is prime itself, as long as a is not a multiple of p, then this is okay. So this is for GCD a p equaling 1. So a and p are co-prime, p is prime, so a would have to be a multiple. So as long as a is not a multiple of p, this is going to work. Okay, so let's use that now to look at an example from the book. Find the remainder when this guy here, 28 to the power of 28, is divided by 13. Okay, so what this is asking is, it's saying, all right, find for 28 to the power of 28 mod 13. What's that equal to? Righto. Well, can we use Fermat's theorem here? So mod 13 is prime, so this is looking good. So if we write this down as mod 13 here, now 28 is not a multiple of 13, so 28, 13, they're co-prime, so that's all right. So if P is 13, then I raise 28 to the power of 13 minus 1, or 12, I am going to get 1. That's what Fermat's little theorem tells me. So I know that 28 to the power of 12 is going to be equal to 1 mod 13. Brilliant. Okay. Now we're going to use this property now to get that up a bit higher and get it closer to 28. So 28, what we do, we'll square both sides. So 24. I know that nothing changes over here because I'm just squaring 1. So that's equal to 1 mod 13. So that's good. Now I've got 28 to the power of 4 to make up. So let's go over here and work out. So 28 to the power of 1, well, that's equal to 2 in mod 13. And if I square that, I'm going to get 4 in mod 13. And if I square it again, I'm going to get 16, or 3 in mod 13. So now look at that. I've got 28 to the power of 24 equals this. I've got 28 to the power of 4 equals this. And I know from this result here that I can now find the product of A and C, and I'll get the product of B and D. The product of A and C is this. So therefore, I can say that 28 to the 24 times 28 to the 4 is equivalent to 3 in mod 13. All right, and therefore 28 to the power of 28 is a remainder of 3 when divided by 13. All right, isn't that a nice result? Okay, well let's have a look at, let's say, should we go to page 64, exercise 5e. Let's have a look at question 1. So we're now in exercise 5e. Let's have a look at question 1a, part 1. And we'll also have a look at, shall we say, we'll just do question 2 also, question 2. So pause this screencast, have a go at those questions, and then come back. Okay, let's have a go at these now. So question 1, 1a, part 1. So we want 3 to the power of 42 in modulus 41. Right, this is prime. So therefore I know that I can write 3 to the power of, in mod 41, I can write this up here. I can use 41 minus, so if this is 41, then I can raise A to the power of 1 less than 41, so 3 to the power of 40, and I know that I'm going to get 1. Now remember, as long as this number 3 is not a multiple of, so just check 3, 41, yep, that is co-prime, so this works. All right, now I've just got to get 3, I need a 3 squared. Well, I get 3 squared is equal to, in mod 41, that's 9 in mod 41. So therefore, I multiply 3 to the 40 by 3 to the 2, and I get 3 to the 42, and that's going to be equal to 9 in mod 41. I'll tell you what, let's do another one. That looked a bit too easy. Let's do C part 1, say. I recommend again pausing at this point and coming back to check. Okay, let's go with C part 1. Let's have a look at what we're asked to do here. We want 7 to the power of 24, the remainder of it when divided by 13. 13 is prime. Notice all these are going to be prime. So we can use, when you see this sort of question and the modulus is prime, think Fermat's little theorem. Okay, let's bring out a different color. So therefore what I know is that in mod 13, I know that powers of 12, as long as 7 and 13 are co-prime, which they are, is going to give me 1. Oh, hang on a sec. I just need to, all I need to do is square both sides, and I've got 1. So that turned out to be even simpler than the first question. Okay, I'll leave the others for you to do. I also said let's do question 2. All right, so let's just have a look at that now. Pause if you haven't done so already and come back. 35 to the power of 32 when it's divided by 11. So I want that in mod 11. Okay. Now I know 11 is prime, so I know that my 10 power, I know that 35 to the power of 10, 35 and 11 are co-prime, so I know that's equal to 1 in mod 11. Now I can get that to the power of 30 quite simply by cubing both sides. So I'm still at 1 in mod 11 when I get 35 to the 30. Once I get there though, I just need now to get 35 squared, don't I? So 35 in mod 11 is equal to 2 in mod 11. And so 35 squared is just going to be equal to 4 in mod 11. So therefore, 35 to the power of 32, when you multiply this by this, will be equal to, when you multiply this by this, is going to be equal to 4 in mod 11. So for question 2, the remainder, when 35 to the power of 32 is divided by 11, just checking the answers in 5e, question 2 is 4. Okay, I'm going to leave it there and leave you to continue and finish now the questions in exercise 5e, and in fact all the questions in chapter 5, and we'll spend a lesson or two when at the start of term 3 just having a look at any problems, any questions that you've got. Okay, good luck with all that. I'll see you for the start of term 3. Enjoy your holiday.